Hello friends, so in this session we are going to discuss about DC to AC converters which are popularly known as inverters. So we'll start with the first variety, that is single phase half bridge inverter. So let's see what are DC to AC converters. An inverter uh, converts fixed voltage DC into desired frequency AC. Applications are adjustable speed AC drives, induction heating, UPS, and HVDC transmission. Right? An inverter converts is missing over here anyway. So classification of inverters, so according to the inverter, there is nature of voltage source inverter or current source inverter. According to connection, we have series inverter, parallel inverter, or bridge inverters. And according to number of phases, inverters are either single phase or three phase inverters. Now, these are the power electronics which are used in the latest inverter which are used these days. These are power BJT, MOSFET, IGBT, and GTU, right? Thyristor SCR are not preferred as they are difficult to turn off. In most of the old books, literature, you will see the inverter with the example of a thyristor, but I don't prefer to show thyristor as a switch when I discuss inverter with the students. So let's see the single phase half bridge with pure resistive load. So this is the circuit of single phase half bridge inverter. Okay, so here what is the requirement? The requirement is that you require a center tap supply with half the voltage, Vs by 2, Vs by 2, and this is the center one, right? And these are the two switches, T1 and T2. Here I have used BJT as a switch. I can show IGBT or MOSFET or GTU also as a switch. The main highlight is that these are the switches which can be turned on and off by sending the signal at its control terminal, that is base over here. So let's see how it operates. So the first switch, that is T1, is on for half the time period and off for remaining half, and the lower switch T2 is off for half the time period and on for the remaining half time period. Now how does it happen? So you can see when the T1 is on, the circuit is completed in this fashion. The same is drawn over here, and it's a pure resistive load, so plus minus V0, which is equal to Vs by 2, comes across here. If I draw the waveform, you can see this is Vs by 2 for the time period T by 2. And as it is a load is purely resistive, current is also of the same nature, same square wave you get, which is equal to whatever is the voltage divided by the resistance. Okay. Now in lower half cycle, that is when the T2 switch is turned on, what's happening? When T2 is off, this circuit is completed in this fashion, and so you have plus minus V0 in this fashion. So the voltage across load is having same Vs by 2, but with the opposite polarity. So the full waveform, this is for first half cycle when T1 was on, and this is for remaining half cycle where the T2 is on. And you can see the voltage and current both are now alternating. If the same pattern switching is continued, you get a alternating voltage as an output. So this is how we have received DC to AC conversion. Though it is a square wave, but it is made up of fundamental sine wave plus its harmonics. So if we filter the harmonics, you get more or less sine supply from it. So this is a square wave inverter, but this is a very fundamental principle of how the inversion or DC to AC conversion is achieved. Now, what if the load is RL? Most of the loads which we use are RL loads, so inductance is there. So in that case, when the switch is turned on, it is all right that Vs, this is the circuit which is taking place over here, and because of which current is rising over here. Now, the thing is that okay, so here when the switch is turned on, you get a square wave rise pulse of voltage, but due to inductance, the current cannot uh, rise immediately. It rises with a lag. Let's say this is a simple way of showing it. And when the voltage at after T by 2, when the switch T1 is turned off, the voltage is now negative. So definitely current has to follow it. Now the thing is, when switch is turned off, this was the direction of flow of current. If this switch is turned off, immediately whatever was the original flow of current, which is still non-zero, cannot suddenly reduce to zero. So that is an issue. So what happens over here? So if there is nothing in parallel with this switch, then this current cannot reduce to zero instantaneously. This leads to very high induced EMF in inductor, and this ultimately tries to force the polarities are reversed, and it tries to force the current in, it tries to maintain the current in the same direction. In doing so, such a high voltage is developed, which may damage the switch keeper. So always we use a diode anti-parallel with this in our arrangement whenever RL load is there. When inductor current cannot change instantaneously, therefore diode is used in anti-parallel with the switch T1 and T2 as shown. In the next slide, I'm going to show you the arrangement. So these are D1 and D2, which are anti-parallel diodes, which are used to release the energy which is stored by inductor. So when voltage reverses and current is not reversed, so this gives the path to reverse the current. I'll show you the waveform. So D1 and D2 are known as freewheeling diodes. You can see when the voltage has reversed, current is still not zero. So at that time, current is reversing in a lagging fashion. So this is the duration when voltage is positive and current is negative. So D1 is giving the path. So negative current is flowing in this fashion. So negative current is flowing in this fashion through D1, and then T1 is on. So when T1 is on, so normal current flows, which is positive in this fashion. When the other half cycle is there, so at that time this positive current has to flow. So that positive current flows in this fashion through D2. So D2 is on, and when that current reduces and reverses, so the D2 is now giving the same reverse current, right? So this is how the D2 and D1 are having the freewheeling action. So this is what happens whenever RL loading is there. That's all about the single phase half bridge inverter with RL load. Half bridge is a simple arrangement, but here center tape supply is required. And the peak to peak voltage you are getting, that is maximum voltage you are getting, is Vs by 2. Right? So you can derive the formula for RMS value of such. So we are not going into the detail of it. This is for quick understanding of the concept. Right? I hope this is good for initial understanding of the topic. We'll continue with a more detailed video in next section. Thank you.